per usual, my memes, Thor. Well, those was pretty great. If anyone lives in Long Beach, that roundabout is a nightmare, but zero faith in the human race. I thought this was pretty relatable for this time in the semester. But you guys are doing great, so keep up the good work. And my last one. If you don't get it, watch Harry Potter and the Chamber of Secrets. Anyway, hopefully those made you laugh. This week we are looking at ANCOVAs, MANOVAs, and then in general, how do we evaluate scientific literature? So it's tying everything together from lecture 1 primarily. In previous semesters, I used to do ANCOVAs and MANOVAs on different weeks, and then you would be responsible for knowing how to run both of those. But given the online format, I don't really think it's necessary to add to your plate because they are more complicated to run in their kind of methodology on how they work, but also they're not as commonly used in research as the other methods or statistical tests that we've used so far. So actually using them if you're going into research, it's good to know that they exist, but there are definitely alternatives to using these types of tests. So I kind of compiled a list of things that I think might be important for you to focus on in terms of what to know. So as always, know the assumptions, right? So how many variables, types of variables, if there's any special tests that have to be done, like sphericity or homogeneity of variance, and then any other characteristics like how the samples were collected. And then also, as far as recognizing examples in research scenarios, that'll go for any of the tests that we've looked at so far, but this is probably most applicable to MANOVAs if you're just reading a research example, because those outputs are a bit harder to digest. But for ANCOVA, it might also be coming up with an example of a covariate, which we'll talk about in a little bit. And then finally, kind of looking at more of the conceptual end, like knowing what the process is, still thinking about, null hypotheses and what they mean in terms of when you get a p-value. So pretty much everything minus having to know how to run the test, which I'm telling you takes out a very significant step. So you'll still have to know how to read the outputs, and I put in some pictures in the slides today that'll hopefully help you guys when you're going through the activity. But these are kind of the main points, which I feel like are pretty much the same for all the tests that we've looked at so far. So it shouldn't be anything surprising. We'll start on ANCOVAs. So the C just stands for covariance. And so basically on our decision tree, we have the same pathway we use for factorial ANOVAs, only we have the presence of an ANCOVA. And you'll see that usually we use factorial ANOVAs when we have 2 or more independent variables. It's yes and no the case. This is the decision tree that the book gives, and I agree with it to a certain extent. And the main reason is this 2 or more independent variables, because covariates, you can have a one-way ANCOVA, you can also have a two-way ANCOVA, right? The number of independent variables can be 1 or more. And I think the reason why it's placed in this position in the textbook's decision tree is because they consider a covariate similar to an independent variable. And its nature is similar to an independent variable, and we'll talk about why, but I wouldn't necessarily classify it as a a leveled independent variable, if you will. Like when we look at gender, we have 2 levels, male and female, right? And covariates don't kind of adopt that characteristic. So kind of used loosely here because you can have one independent variable and a covariate and still have an ANCOVA. So use this loosely, but I think when we talk about the methodology, that part will make sense. So what is a covariate? I think that's a good thing to address first. Basically, if we kind of think about covariate in similarity to covariance when we talked about regressions several weeks ago, right? That covariance basically was looking at relationships between variables and the ability of a certain number of variables to predict a dependent variable. So this is kind of similar in the respect that if you kind of separated out those components of a regression and you're only looking at one variable that might have an effect on a dependent variable, that's what the covariate is in ANCOVAs. So it's just a variable that might account for an observed difference in the dependent variable, but based on an independent variable manipulation. So in the sense of, is it parametric or non-parametric, covariates are always measured. So they will always be classified as parametric data, right? Which is our ratio or interval data. For our class, we're pretty much always going to use ratio in terms of parametric data. Like I said, it's similar to an independent variable in the sense that it's controlled, but it's not an independent variable inherently. And as far as it affects, right, it's similar to a dependent variable because of its measure type, but it's going to affect the potential dependent variable outcomes, but it's not, again, classified as a dependent variable. So a covariate is its own type of variable. Okay. Again, to reiterate, we use the covariates to account for potential differences between groups. And the way that it works in the analysis process is we use the covariate to make our groups more comparable. So sometimes this will be used in a pre or post test situation. When we can use the pre-test as the covariate, oftentimes we might just have 2 independent groups, and then we have a covariate that we measure for each of those groups and then use that as the covariate. So I have a few examples to kind of illustrate those differences. The first being, if we were looking at this research question, what are the different effects of various antidepressants on depression when controlling for how long a person has been depressed? So usually when I pose an ANCOVA question, I'll typically add in a statement like you're controlling for, or you're considering, or typically X variable has an effect on Y. So you can kind of identify them in that respect. But in this example, right, again, ANCOVAs are going to use independent samples, which I think gets a little bit confusing to some people when we look at the pre-test, post-test situation, but I'll get to that in a second. So we're going to have independent samples for this, and let's say our independent variable is different antidepressant medications. And so we'll have, let's say we have 3 different samples and each person is trying a different drug. Okay. Our dependent variable would be on their depression. So we would give them, I think there's like a survey or a test that you can ask somebody, and it identifies like what types of symptoms they have, whether they're behavioral, cognitive, motivational, etc. So we'd give them a self-scoring depression scale and they get a depression score. This is kind of a sad example, but our covariate might be a confounding variable or an extraneous variable. If you guys remember back to the first lecture, we said extraneous variables are things that could interfere with our dependent variable outcome, right? But they're not necessarily taken into consideration in the inclusion or exclusion criteria. So ANCOVAs are nice because we can kind of account for measurable extraneous variables. So maybe a person's level of depression or how long they've been depressed might affect the effectiveness of the medication, right? So in this case, we could say the time that a person's been depressed could be considered a covariate, right? And then when we end up looking at the null hypothesis, it's basically exactly the same as a regular ANOVA, but again, you're just kind of adding this little tidbit at the end. So the null hypothesis, again, always argues there's no significant effect, right? So we'd say the type of antidepressant medication has no significant effect on depression when controlling for how long a person has been depressed, right? So you're just adding in that extra consideration factor. Any questions on this example? We'll do some more. So hopefully it'll start clicking. Next example I have is a pre-test, post-test situation, right? So, and this is where I think people tend to get a little bit confused because they're like, well, pre-test, post-test, that's using the same person for two measurements. And this is true, but this is also why we say that the covariate is a pre-test. So technically, you've only measured the person for like the dependent variable measurement, you've only measured them one time. And remember, the covariate is always measured, but that's kind of like we're controlling for the starting point of a person as a possible effect on what the outcome might be based on your grouping of your independent variable. So in this one, I have what are the different effects of various stretching programs on flexibility when controlling for pretest flexibility. So I had used this example previously in the semester saying like if you have someone who's really not flexible and it's because of structural constraints, you wouldn't really expect them to have a lot of flexibility post-test, right? Or it might explain some of the variability that they have in their post-test. Unless you also have like a really effective stretching program, in which case that would be a result of the effect of the test. But someone's starting flexibility might have an effect on the outcome of the stretching programs, right? So in this case, again, we'll say we have independent samples, and we'll say we have 3 different stretching programs, which I think I use it in a figure later in the PowerPoint. So I had like a control group where they don't stretch at all, P&F stretching, and static stretching, okay? We're kind of limitless on the types of stretching programs we could do, but let's say we have 3 groupings of the stretching program, and we measure everyone's flexibility by looking at a range of motion test, for example, right? And so then we would say, we'll stretch them before their program and take measurements, and then we stretch them after the program to get their measurements. Okay, but we're using the pre-test flexibility to kind of control for the flexibility that we see in the post-test measurement. So as far as a null hypothesis goes, we're basically saying the type of stretching that they engage in has no effect on their flexibility when we consider their pre-test flexibility, right? And then obviously the interpretation of the p-values goes the same way that it has been for all of the tests we've been working with, right? So I think the part where we kind of dive in a little bit more is like, what do you mean when you're controlling for the covariate? And that's where the process of the analysis comes in. So before I move on to that, are there any questions so far on this example or the other example? Okay, so analysis. It's a 2-step process. So obviously we have to check our assumptions first. We'll go over those in the next slide. But an ANCOVA essentially mixes a linear regression analysis with an ANOVA. And that kind of makes sense based on the types of variables that we have. Because if you remember in a regression, both the independent and dependent variables had to be parametric data, which is often why the covariate is seen as an independent variable, because it's compared to the dependent variable in a way that it acts as an independent variable. Because you remember when we make regression equations, the independent variables are represented by the B coefficients that we end up getting out of the regression analysis. So the way that we control the dependent variable outcomes using the covariate is that we stick these two things in a regression and basically get a predictive equation. So then we can alter, right? Remember we had applied the use of the regression equations before to predict certain values of a dependent variable, and then we were like, what's the actual versus the predicted one? So that's what the regression analysis does, is it uses those covariate values and the regression equation based on its relationship with the dependent variable to adjust the dependent variable values. And then those adjusted dependent variable values, based on their classifications from the independent variable, go through an ANOVA. Right, so that's where we check the between subject analysis to see, are any of the groups, do their means, are they similar enough that we would say they're equal, or are they different enough that they're significantly different? Okay, so two-step process: regression, where we correct the dependent variable using the covariate, and then the ANOVA, where we actually compare independent variable groups using those adjusted dependent variable values. So in order to do this, we have to have our assumptions. Two that you know already off the bat are we have to have a normal distribution and random sampling. Okay. If we have a between subject study design where we have independent samples, that automatically tells us we're going to have homogeneity of variance. Okay. And this part can get a little bit confusing for students, at least it has in the past, because there's more than one homogeneity of variance that shows up in the output. So I'll identify which one you guys are looking at, but it's the homogeneity of variance for the between subject design. Okay. We also have a new assumption called the homogeneity of regression. So you'll remember when we make a regression, we have a line of best fit, and that line of best fit has a slope, right? And basically all we're doing in this homogeneity of regression, kind of think of it similarly, homo means same. You want the slopes to be relatively the same, right? Or parallel slopes, if you will, so that the rate of change in each of your independent variable groups is relatively the same based on that covariate relationship with the dependent variable. And I have a picture of this, so hang tight. Okay. Lastly, we have a new assumption of independence. And this is important because we have to make sure if the covariate is a measured response, right, we have to make sure those measurements are not going to be affected by the independent variable measurement. So let's say for some reason we wanted to look at height changes in individuals, or our between subject factor maybe is gender, and how height changes are kind of affecting or are being affected by gender, right? If we used a covariate of weight, we know that weight and height do have a correlation, but generally males tend to weigh more than females because they have more muscle mass, right? So in that case, you would have to be kind of careful to make sure that gender also doesn't have an effect on weight, right? So that it's not skewing your results. So the independence we usually do by doing a one-way ANOVA between these two variables, and I have an example of that later. Okay, but these are the main ones that you have to meet. If you wanted to add in like a parametric dependent variable or between subject sampling, that type of thing, so I have those two added down here. You can add them, but I put asterisks because they're not as important to list and they'll vary based on the between subject, not so much, but the types and numbers of variables that you're working with might vary based on the type of ANCOVA you're running. So these first 5 are the main ones that you want to focus on for this test. All right, so going into the homogeneity of regression, this assumption is run by itself in its own test. And basically what it looks at is the interaction effect. So I have it highlighted in here. It looks at the interaction effect between your independent variable and your covariate, okay? Which doesn't sound intuitive based on how it's written, because really what we're looking at is the slope of the regression line. And what goes into the regression is the covariate and its relationship with the dependent variable, right? So that relationship is going to create a line of best fit based on your data. And then the reason why we look at this interaction is we say, if we have this regression line of covariate relationship with the dependent variable, how do those lines match up when we organize by our, where's my pointer? Well, how do those lines compare to each other when we organize by the independent variable, which in this example is sport, and in this case the covariate is mass. So really we're looking at and dependent variable being caloric expenditure, right? So covariate and dependent variable, we're comparing the regression lines for these two things while kind of compartmentalizing our data by sport, if that makes sense. Okay, so the null hypothesis for homogeneity of regression is you're assuming that the regression slopes are equal between independent variables. Okay, so typically this will be what the output looks like that I'll give you guys, and again, you're looking for this little interaction here. And what we're interested in is the p-value. So in an ideal world, this p-value is greater than 0.05, similar to a lot of our other assumption tests that we've done in the past, because that means that we've met the assumption, right? In this case, it would mean that the slopes are equal to each other, right? Or the rate of change in which the dependent variable is changing compared to how the x or the covariate variable is changing are relatively the same across the different sport categories, okay? So when you look at this output, you really want that interaction p-value to be greater than 0.05. However, I will say I have not had very much luck in finding examples where this holds true. And I'll show you with the, I think I have an example later, but there's some times where it looks like graphically your lines are parallel, but you get a significant p-value, in which case it's saying the slopes are not parallel. And so based on that variability, I've kind of made it for this class where you ignore the p-value, even though that's the way we assess it. And typically when you would have significantly different slopes, you would have to stop the analysis and kind of reevaluate your situation. But for this class, whenever you see a non-significant homogeneity regression, just accept it and continue with the analysis, because even finding practice data sets on the internet has not afforded me any comfort in the variability that I see with this test. So a graphical representation would kind of look like this. So again, we kind of use these different sports. In this case, we have rowers, swimmers, and runners. And for each of those sports, we're plotting pairs between our covariate mass and the dependent variable caloric expenditure, right? So each of those pairs is going to give us a dot, and the kind of trend line of those dots within their respective groups will give us our regression lines. So you can see in this one, the lines are fairly parallel. there's a potential that we have a significant interaction just because this red line is intersecting the blue and the green line. But as you can see in our previous slide, we had a non-significant p-value. So you could see that that's a perfect example where the two tests don't really align with each other. But for this test, when I ask you for a p-value, this is what I'm looking for. Okay. Any questions on homogeneity of regression? All right. So the next assumption that you would have to test in SPSS is independence, right? So making sure that the independent variable does not have a significant effect on the covariate. So the way that we do this, like I said before, is you run a one-way ANOVA where you list the covariate as the dependent variable. So this is where I lose some people because they're like, but the covariate's not the dependent variable. And I'm like, yes, I know, but the covariate is a measured variable, in which case we can figure out if the independent variable has an effect on the covariate. So in this case, you would read the one-way ANOVA, but just keep in mind when you see the dependent variable label in the output, it's really the covariate. So it helps to write down what your variables are when you're running the analysis. But basically, we get a one-way ANOVA output where we have to evaluate homogeneity of variances for the different groupings of the independent variable, right? So in this case, we would say there's equal variances amongst mass measurements for sport, right? Because we have a p-value greater than 0.05. This is also where I lose some people because you'll remember that one of the other assumptions for an ANCOVA is that you have to have homogeneity of variance. This is not the p-value for homogeneity of variance for the test. This is just so you know what the independence is, right? So if we have a p-value greater than 0.05, we can look at the ANOVA output p-value, right? If the p-value is less than 0.05, that's when we look at the Welch's p-value. So that process still holds for the independence test. But really what we're interested in is this p-value that tells us what the between group variances are, right? So in this case, p is greater than 0.05, which is a good thing, right? Because that tells us that we've met our assumption or that our independent variable has no significant effect on our covariate measurements. Okay, so when I ask for a p-value for independence, this is the one that you report. If we had a p-value less than 0.05, that means that we violated the independence assumption, right? In which case our data, as far as our dependent variable goes, might get skewed when it's run through the regression process. Okay, so that's independence. Those are the two. Usually in the outputs that I give you guys for ANCOVAs, I'll put homogeneity of regression first, followed by the independence test. And then the last thing that'll show up in your output will be the ANCOVA, which is the main effect that we're interested in. Okay, so in this one, you'll also get a Levene's test of equality of variances, right, or homogeneity of variance test. This is the one that you look at. And that's why I put the box with the arrow. Okay, so when I ask you what's the p-value for homogeneity of variance for an ANCOVA, you have to scroll down past that independence homogeneity of variance first. Okay, and it's the second one that'll show up in the output. So in this case, similar to other ANOVAs we've looked at, you still want greater than 0.05 because that means you have equal variances amongst your groups. Okay. The last thing is the p-value for the main effect of the test. So that'll be in our test of between subject effects. And if you recall, our independent variable was sport. Now, the covariate also gets added to this this output because, like I said, it's often considered very similar to an independent variable since it's controlled for. but we really don't pay attention to this in the output at all. All you're interested in is this sport row, right? Because that's the independent variable you're trying to see. Does that independent variable have an effect on the dependent variable when we consider the covariate, right? So in this case, our p-value is 0.003, and we would end up saying, right, the null hypothesis, remember, for ANCOVA is the same as an ANOVA, but we're considering the covariate. So in this case, we would say if this is less than 0.05, right, we would need to look at post hoc tests to see where the significant pairs are, but we generally could say that sport has a significant effect on caloric expenditure when we consider body mass of the individuals, okay? So it's a very piecewise process, and I think the flow is pretty simple because you're just kind of connecting dots on ANOVA outputs, and you're just adding a little bit extra to it. Okay. There are some special considerations for ANCOVAs. One being that they're not always the most appropriate test, and that is okay. So like when I'm going through some of these examples and I notice the p-value doesn't match what I'm seeing in a graphical representation, maybe there's a problem with the homogeneity of regression, right? And we just shouldn't use an ANCOVA, right? So I use this example of the stretching programs where we're technically saying, like, I want to control for a pre-test measurement, right? And these were the outputs that I ended up getting. Graphical representation, you can see the lines look pretty parallel to each other. The red one might be a little bit off, but for the most part, they're not intersecting. Doesn't look like there would be an interaction effect. But when you look up here at the interaction for our homogeneity of regression, you'll see it's significant, which basically means the slopes aren't parallel, right? So visually, it's kind of confusing because the p-value doesn't agree, right? And so if this is the case where you have a problem with an assumption, like I said, for this class, we kind of just ignore that we violate homogeneity regression most of the time. But if that's the case, you can always just change the test that you're using. So maybe you can't control for a pre-test measurement, right? Maybe instead you use a control group, right? Because we technically have a control group in here where there's no program, right? They don't go through any specific stretching. And we could still compare that group to PNF and static stretching in just a regular one-way ANOVA. We could also do a two-way ANOVA if we wanted to, and say that one variable is, in this case, it would be a mixed factor, right? Because we could say one variable is our stretching program. That's a between subject factor. But we could also have the pre-test and post-test factor, which would be a within subject factor. Right? So the ANCOVA is not always the end result. And I think that's okay. The pro to using an ANCOVA is that it gives you more statistical power, simply because it kind of decreases the unexplained error, unexplained variance that we usually get in tests, right? And that's because, like I said, you can use extraneous variables as covariate measurements. So it has a pro to it, but kind of taking it out also doesn't necessarily hurt the test you're using, as long as you address the limitations that you might have and you control for those limitations to some degree, right? Or as best as you can. All right, that's ANCOVA. That's it. We're going to move on to MANOVA, but are there any questions before we jump forward? I'll take the silence as a no. All right. The rest of this actually isn't too complicated. I say that loosely, but a MANOVA isn't really different from a lot of the tests that we've looked at so far. The M just stands for multiple. That's the big difference, right? So question for the people, up to this point, how many dependent variables have we been working with? Whether we look at a t-test, ANOVA, factorial ANOVA, or an ANCOVA, Chris is holding up a 1. That is correct. What does the multiple stand for? Multiple dependent variables. That's literally the only difference. Okay. So, aside from a few conceptual differences, the way that you determine what tests to run is exactly the same. But if you identify multiple dependent variables being measured, you know the name of the test, you just add MANOVA instead of ANOVA, right? The same thing for if you have a covariate present, it's a MANCOVA, right? Which always makes me think of man caves, but that's off the point. Okay. But generally what we say is like the number of independent variables determines the type of ANOVA, right? So we said if you have one independent variable, it's a one-way. If you have two, it's two-way. If you have three, it's three-way, right? But also the types of samples kind of dictate how we label things. The number of dependent variables tells us what type of test we're using in terms of if it's a univariate, meaning one dependent variable, or a multivariate, which is two dependent variables. And you've seen multivariate pop up before in the repeated measure outputs. If you guys recall, there's always like this awkward multivariate test kind of lingering at the beginning. And I always told you just skip over it. We don't need it yet. That's for MANOVAs. Okay. So what type of variable do you think the dependent variable will be? It's the same as it has been, right? Measured variables that are parametric. We could also call them scale in terms of SPSS, or their ratio or interval data. Okay, so it's all the same. We just add more, right? So in terms of our decision tree, okay, we do have a little bit of play, and this is kind of the only exception, is t-tests can also have MANOVA classifications. There's just not really a good word to use for them. Okay, so you can have potentially one independent variable that only has two levels, or you're measuring two groups essentially, but you have multiple dependent variables. You could either run a whole bunch of different t-tests, or you can still put that through a MANOVA. The results, the way that you read them is a little bit different, but it is possible. Okay, but basically you could see we add multiple dependent variables, we just change the name at the bottom. MANOVA, MANOVA, MANOVA. That's it. Okay. So this is the flow chart and the decision tree that I updated in your guys' files this week. Okay. So with MANOVAs, in terms of assumptions, the assumptions that you guys have learned for one-way, two-way, or this week we're adding the ANCOVA assumptions, all of those stay the same when you figure out what MANOVA you're running. So it's kind of a stacked approach. You say, all right, well, I know when we only have one dependent variable, these are the assumptions I have to meet for a given test. And then for a MANOVA, you just add a couple of assumptions. Okay, so MANOVAs adopt the assumptions of their base test, right? And then we just add multivariate normality, which regularly we look at a two-dimensional bell curve. In this is very complex, but in a MANOVA, we look at a three-dimensional bell curve where we're taking all of the different dependent variable measurements and we're putting them into this crazy thing. Okay, this isn't tested in SPSS. So typically in previous semesters, I just told the students check the univariate normality for each dependent variable, where we would, take what's the skewness of the sample divided by the standard error of the sample, right? Or same thing for kurtosis. And then they would just say, are any of those dependent variables not normally distributed? And they would flag them. But for this, just know multivariate normality. You don't have to know how to calculate it. You don't have to do any calculations whatsoever, right? Just multivariate normality. And in addition, we have one more assumption we add, and that's homogeneity of variance covariance. So kind of similar to regular homogeneity of variance, but rather we're looking at the correlation between dependent variables and if that's the same for all of the groups. And this is beyond the scope of this class and a little bit too complicated to explain, but usually we test it with boxes tests. So that's another thing that you might have seen pop up in the repeated measures test when we have run stuff through outputs before. Again, you don't need to know how to analyze this, but typically if homogeneity of covariance is violated, that means that one of the independent variables has violated the homogeneity of variance assumption. So typically you can look at Levine's test to correct for violations of the covariance, but in general for you guys, all you need to know, MANOVAs adopt the same assumptions as their base ANOVA test, and you just add multivariate normality and homogeneity of variance covariance, period. That's it, okay? Once you have your assumptions listed, how does a test work, right? So basically, in a very complex way, there's a multiple regression that's used to make this composite dependent variable. So let's say we have 5 dependent variables that we've measured. This regression merges all of those variables into a single variable. And then that variable is basically run through multiple different ANOVAs in some way, shape, or form, right? To see if there's any independent variables that have an effect on this virtual dependent variable, right? And that ends up giving us this omnibus F ratio. I love this word. But what the hell does that mean, right? We know F ratios are measurements for ANOVAs. So the null hypothesis basically says, potentially we could have multiple independent variables, which is why I put the S in parentheses, but the independent variable, we say, has no significant effect on any of the dependent variables. That's kind of how this extrapolates, right? So if we take a mutually exclusive statement to the null hypothesis, we get our research hypothesis. And so if you get a p-value less than 0.05 for this omnibus F ratio, which I'll show you an example in a second, you would say p-value less than 0.05 means significant, right? That the independent variables have a significant effect on at least one of the dependent variables, right? So there's something significant somewhere in this big analysis, okay? Do note though, this omnibus F ratio p-value is not the end of the test, okay? So it doesn't prove anything because there's too much involved in this big process of combining a dependent variable. We just know something is significant. So in a way, it's kind of like when we say, oh, an ANOVA is significant, but we don't know which pairs are significant. In this case, we say the multivariate test is significant, but we don't know which univariate tests are significant. So it's also a step-down process similar to the ANCOVA, right? So the first thing we evaluate is this omnibus F ratio, which is in that multivariate test, okay? If it's not significant, you stop the analysis because we're saying, well, none of the independent variables have a significant effect on the dependent variables, so we don't really need to continue the analysis. If, however, this omnibus F ratio is significant, again, that indicates there's at least one independent variable, if there's multiple of them, that has an effect on at least one of the dependent variables. So this is where we go into the univariate tests, basically looking at individual ANOVAs of each independent variable's effect on a given dependent variable, which we know there's multiple, so that's where this test kind of gets expansive very quickly, right? But then from there, you guys know how to read univariate tests, right? And you say, well, is this independent variable, does it have a significant effect on a dependent variable? If it does, you go to post hocs. If it doesn't, you accept the null hypothesis and move on with life, right? But the thing is that you're going to be checking this for multiple dependent variables. So there's a lot of different p-values. which I know you guys love p-values by this point. All right, so let's pull this together in an example because that's a lot of words and visual representation helps. Okay, so I have 3 practice problems in the PowerPoint. We're only going to go over this one, but in the other 2, if you look in the notes section, I've listed out what the independent variable is, what dependent variable, what the assumptions would be, what type of test you would run, so you can check your answers to make sure that you're reading it right. Okay, but this is our scenario. You are interested in seeing if individual or class training has an effect on, this would be body fat composition, okay, VO2, and stress. Each participant is randomly split into one of 3 groups, so that already tells us we have a between subject factor, or independent samples, right? And they undergo each of the tests to obtain measurements of our dependent variables, right? Basically, you want to see if there's any significant differences between the groups amongst each of the measurements. Okay, so in your guys's, what is it called? Your activity this week, this is what you're doing. You're saying, what's the independent variable? How many levels are there? What type of data is it? What's the dependent variable? What type of data is it? How do we collect our samples? Is there a covariate, right? So if you look in the notes section on the PowerPoint, I've kind of highlighted these things for you, right? As far as training program goes, this used to go with a data set that I don't have, or I don't give to you guys anymore. But the training set or training programs in this case would be individual class, or an individual doing their own training, training happening in a class setting, and then a control group where maybe nobody does any training whatsoever, right? So in this case, that independent variable would have 3 levels, okay? And we would say it's non-parametric or nominal because we're categorizing people into groups. And we already said that they're randomly split, so we have independent samples, right? In addition, our dependent variables, like I said, are body fat composition, VO2, and stress. So automatically 3 measured variables, 3 dependent variables, that means we have a MANOVA, right? You just pair that with the independent variable information you have with no covariates because we're not saying we're controlling for blah, 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 right? So we have a one-way independent samples, right? Or a one-way between, or not between, what am I saying? Independent sample, or you could say simple, that's what I was looking for. Simple one-way MANOVA, right? Literally the only difference is that you have multiple dependent variables, okay? So as far as the assumptions go, all the same as a regular one-way ANOVA, right? Where we have normal distribution, random sampling, homogeneity of variance. Those are the key 3, right? You could also tag in independent samples, totally fine. And then we add in our 2 MANOVA assumptions, which is multivariate normality and homogeneity of covariance variance, right? That's it. Super easy, right? Yeah. Okay. The analysis part is where it gets a little bit trickier, and we'll go through that. So as far as the results go, the first test you look at is the multivariate test because that gives you the omnibus F ratio, okay? So in our class, each of these different omnibus F ratios combines the dependent variable in a different way. We don't go into how this happens. So typically, the top 3 are the more commonly used ones. And the professor who taught this class before me always just said, just average the p-values, and more often than not, they're always equal to each other. So, but we would take the average of the 3 p-values, and then basically that gives us our omnibus F ratio p-value, right? So saying, does at least one dependent variable, is that significantly affected by an independent variable manipulation, okay? So in this case, because p is less than 0.05, we say we have a significant effect in our multivariate test, and at least one of our univariate tests for one of our dependent variables should be significant, right? So then we go into the univariate test process. But remember, we have 3 variables. That means that one-way ANOVA is amplified 3 times. Yay! Okay, so we have, this is Levine's test. What? Yeah, so we have Levine's test for each of our dependent variables, right? Because each of them is going to lie on a different distribution, but we're still splitting them up in the same respect, right? So remember, independent variable was training. And so basically we're saying within each of those different training groups, do we have homogeneity of variance when we're only looking at the body fat measurements, right? In this case, P is less than 0.05, right? So we would say equal variances for body fat. And then we look at VO2, right? And we say, are all of these training groups, do they have equal variances when we're looking at just VO2 measurements? P is greater than 0.05, so we have equal variances, right? When we look at stress, you can see that this has been violated. Now, in a multivariate test, we don't get a correction for Levine's test for the univariate test. So typically, when I showed you the example in the ANCOVA, right? Typically, you have Welch's test that you can add in, and then if you violate homogeneity of variance, you just look at Welch's test. Because there's no correction for this, what you would have to do is look at stress as a univariate test separate from the multivariate test. So basically, you'd run a one-way ANOVA for stress by itself. So that way you can get the correction for Levine's test, okay? But generally, the number of variables you have is the number of assumptions you have to check off, okay? From here, once you know if you've met your homogeneity of variance assumption, right, you would then look at the test of between subject effects, which there's a lot of crap on this table that you don't need. All you're interested in is what your independent variable is, right? So if you have multiple independent variables, that means you're going to have more than one of these, right? And they're just going to be stacked on top of each other. But you can see you get the univariate test, right, based on this grouping for each of your dependent variables. So when we look at the p-value for body fat, right, we read this very similarly to a regular one-way ANOVA, right? And we say, well, p is not significant, right, or it's less than 0.05. So in this case, we would say the type of training has no effect on body fat and just stop that analysis there, right? We can then look at the dependent variable of VO2 and we see P is less than 0.05, right? So we say, or it's greater than 0.05, my bad, right? So then we accept the null hypothesis and we say training has no significant effect on VO2, right? And then we look at our last dependent variable, which is stress, and we see that P is less than 0.05, right? Which means we have a significant effect. So in this case, we would say training has a significant effect on stress. And we know we had 3 different levels of our independent variable of training. So this means at least one pair of our groups is significant, right? So that's when we'd have to look at post hoc tests, and you guys know how to read post hoc tests, right? So basically it would say, is there a significant difference between those little pairwise comparisons of like not having class versus individual training, not having class, and being in a class setting versus individual training versus class training, right? So all those glorious pairwise comparisons you would look at if you get a significant univariate test, okay? Now, similar to ANCOVA, actually, before I keep going, because we're almost done, does anyone have any questions so far on the, like, reading the outputs or anything? I tried to simplify it with the red boxes, so hopefully that helps. Okay, so similar to ANCOVAs, MANOVAs are not always the answer to all of your problems, Okay, and you'll see that actually in some of the article examples I gave you guys this week for your activity that you'll be analyzing. So alternatives to MANOVAs are just running a lot of regular ANOVAs, right? And you run that ANOVA for each of the dependent variables separately. So an example that I've done in research recently is, and Carolina, if she's still here, yes, she is. She worked on me with this research project last semester where we were looking at standing long jump. And we had different attentional focus cues given to people. So it's technically a within subject study as far as what the different independent variable groupings would be. And then we had a lot of different measurements. So we could look at jump distance, we could look at muscle activation in like 8 different leg muscles. We could look at kinematic data as far as like how do their knee angles change. We could look at force data, right? All of these different dependent variables stack up very quickly. And the MANOVA isn't always the answer to analyzing those, because when our dependent variables basically get compiled, if they're not kind of operating on the same wavelengths, it actually could make your data worse. Or sometimes you won't identify significant differences when there actually are significant differences. And so in that research study, I wouldn't choose to use a MANOVA, personal preference, but instead, I would just run a separate ANOVA looking at, okay, how do the different cues affect jump distance? And that's one test. And then I'd say, how do the jump cues affect knee flexion angle? That's another test. How do the jump cues affect quad activity, right? And you can kind of separate each one and do a different single ANOVA for each of those dependent variables. The problem or potential problem with that is you can increase type 1 error. But like I said, it's a very, very widely practiced in literature, which is why I'm using that for my particular study. But that's MANOVAs. So I have 2 other examples for you guys to work through or kind of look at. Again, the answers are in the notes section in the PowerPoint. And then lastly, for the evaluation of scientific literature, you'll get 2 articles to look at this week. I actually gave you 5, but you pick 2 that you want to read. But basically, all I want you to be able to do from that is kind of, again, tie everything back together. So you'll look at the methodology, and based on the information they give you, figure out what are the independent variables, what type, how many levels, what are the dependent variables, what type of data is it, how are the samples collected, right? And then you'll criticize that methodology and say, are there any extraneous variables that these people didn't consider? Or are there any limitations to how they gathered data? Because the thing is, there's always going to be a limitation, but it's what you do with those limitations, right? Did you address them to the best of your ability in the setting that you had, right? Because I think one of the examples I gave you guys this week is with Parkinson's patients. And it's like they can only take their medications at certain times. And so the timing of medication might have been a confounding factor for whatever measurements were being given, right? So keep in mind, sometimes the limitations are out of your control, but they also provide a basis for what you study next, right? They provide a foundation for a new research question, because you could say, this article didn't address this problem, but me as a researcher, I can address this problem in a different situation, right? Maybe I mimic certain characteristics for the subjects, and I keep the controls the same, which is basically how I built my standing long jump study that I just gave an example of, right? The only thing I'm changing is I'm adding on more dependent variable measurements because muscle activity hasn't been looked at in that area of research, but also looking at the types of cues that were used. Those haven't been looked at before, right? So limitations provide a possibility for expansion, which is always a good thing in science because we're always learning more, okay? So With that, that is our last slide. We finished in an hour and I'm really proud of myself. So, do you guys have any questions before we take off? Dog! Oh my god. Hi! Both of my cats are curled up next to me. I'm gonna show because they're cute. Wait, I can't see my screen actually. Hold on a second. I'll stop sharing. Kitties! Yay! Anyways, any questions, you guys? This is the last major content. Yeah, go for it.
So here's the thing for covariates. So I read an article not long ago that was looking at the effects three medications have on, I believe, knee pain, how it alleviates it. And so would the covariate of that be because different doses were administered for each medication? So would that be covariate, the amount of the amount given?
The amount given would probably be more of an independent variable. But if you want to use a covariate example, let's say we took people's pain levels prior to them being medicated, that like pre-pain measurement would be a covariate in that example. And then we would just say, all right, based on their starting pain level, how did their pain level change based on the dosages that we gave them? Did that make sense?
I'll just figure it out later. Yeah.
Okay. All right. So dose would be your independent variable. And the incremental levels would be the levels of that independent variable. But if they took pain level prior to any medication whatsoever, that would be the covariate, if you're applying that to a covariance example.
So covariate is typically done like a measurement before any type of testing is done.
If it's a pre-test, post-test type of situation, yes. But I have several examples between your quiz and what is that called? Your activity. There's 2 ANCOVA examples, so hopefully like one of them is a pre-test, post-test, but the other 2 are not pre-test, post-test, so hopefully that'll give you some more context on how to read those ones. All right. Okay, guys. This is the last major content, so after this, it's all review. Have a great Thanksgiving. Don't forget, even though we don't have class next Monday, your assignments are still due on Monday. Okay, so I know you lovely procrastinators exist out there, but don't save the activity till the last minute. I said that in the activity video. I also said it in the post I made yesterday because it is long. There's a lot of blanks, but it shouldn't take you any more time than you usually take. So I'm just saying if you don't get to a certain chunk of questions, it could be detrimental to your grade. But there's a lot of points possible this week, so it won't kind of hit you as hard as it would have in previous weeks. All right.
One more thing. Yeah. It's concerning the activity that's due today for the output.
Sure.
So in the